how I can map the two vertical lines to, let's say, two lines, two hyperbolic lines where one is vertical and one is a semicircle. Thing is, okay, well, I want to send a line to a line. I want to send one of the vertical lines to a vertical line. I want to send one of the vertical lines to a semicircle. Thing is, okay, well, I want one hyperbolic isometry on the upper half plane to do the trick. Thing is, all right, when we look for all these isometries, thing is, we can't just send random, well, we can, but there are lots of things that we want to keep track of right now. We have two lines, two hyperbolic lines. We want to send them to two hyperbolic lines. So the key is, right, let's see if I can find 3 points and just keep track of those. That's the key. Any suggestions? Let's say if I want to send two of my white lines to two yellow lines, and I'm just going to use the word line to mean geodesic, I want to say, all right, well, I want to look for a specific map P or matrix P. Let's say I want the one on the left to go to this and the one on the right to go to this line. And I want P to do both of these at the same time. What's anything, well, you don't have to give me the entire answer at once, but what are some of the things you want to keep track of? Let's say if I call this one L1, L2, L3, L4, let's call this one L5 and L6. And I say, give me a map. I'll just write P as meaning the map and also the 2x2 matrix that sends L1 to L3 and L2 to L4. The reason why I'm looking for this is because I can't grab all the possible lines on the upper half plane and then say, hey, I'm taking the composition of these two, two reflections. Let's say if I actually work this up for L1 and L2, which seems a little bit easier to deal with than the other cases, is there a way I can say, all right, I do know that the composition of reflections about L1 and L2 give me a parabolic isometry. Then what you can do is you can say, well, actually, you know what? If I conjugate this to anything I want, meaning I can map these two lines to anywhere I want and say, all right, well, reflections about lines will still be reflections about lines. Taking the composition wouldn't change anything. The thing is, these two isometries, orientation preserving isometries in the composition, will be either both parabolic or both hyperbolic or both elliptic. So, the key is, okay, well, if I prove it for a very specific case of two vertical lines, how do I map L1, L2 to L3, L4, in that specific order? I mean, and of course it doesn't matter. You can change the order of L4 and L3, but what's a way to map the two lines, L1 and L2, to L3 and L4? That's the key to proving it in general. And then you can see if there's, let's say, call Q another map where you map L1 to L5 and L2 to L6. They're not very different. One thing you could do is, actually, I'm going to hold my tongue for a little bit. If you're completely lost and have no idea what I'm saying, be honest and tell me in the chat. If you think you know the answer and you want to double check with me, you can also use the chat too.
No, let F be a composition of two reflections.
You just joined. What we're talking about is problem number 1. How do we prove this in generality? I got something in the chat. All guesses. Okay, there are a lot of guesses. Okay, some sort of isometry. Inversion. Okay, inversion's an idea. What I want to do over here is I want to send L1 to L3 and L2 to L4. Okay, well, we do kind of know how lines and circles are mapped to lines and circles. For example, if we take the horizontal translation, we know what the shape looks like. In our eyes, we just move everything to the left or the right. Dilation also, the shape doesn't change much. inversion was one of the things that actually, was a little bit tricky to see. Some of the lines went to circles, some of the lines stayed lines, and then there were circles that were mapped to lines or circles. So inversion was the one that was a little bit tricky. So here, if we want to map L1 to L3 and L2 to L4, there has to be some sort of inversion involved. Yes, that's true. Thing is, when it comes to inversions, okay, well, we have to know what line we're trying to, invert. And also, when we do inversion, it's always about a very specific point. The thing is, all right, well, what point do we want to map where? Here, I'll tell you what the key is. I think I can be more impatient, but I think you guys want to know the answer too. So I'll say this is the key. When I'm looking at a pair of parallel lines, that means that they're either going to meet at infinity or they're going to meet at a point on the boundary of the upper half plane. So in the case of L1 and L2, they actually meet at infinity. Where L3 and L4 meet, well, they don't meet at infinity because one of them is a semicircle. It looks finite. Thing is, they meet at this point. I don't know what this point is, but I'm going to call it x equals c. Or, well, actually, it's not a line, so let's not call it x equals c. Let's call this point c comma 0. And what we're trying to do here is we're trying to say, all right, well, L1 and L2 form a pair where they meet at infinity. Now I want to send those two lines to L3 and L4. And I don't know, where the other points are going to go to, but wherever L1 and L2 met, they actually met at infinity. We're sending that point to the point where L3 and L4 actually meet. Now, they meet at the boundary. So here, when I'm looking for this map P to send L1 and L2 to L3 and L4, what I'm also trying to do is I'm trying to send infinity. So this is the point of intersection where L1 and L2 are intersecting. Well, that point must go to the intersection of L3 and L4 as well, right? You have two lines or two curves that meet at a point. You're mapping the two lines somewhere else. Well, the point where L1 and L2 meet has to go to the point where L3 and L4 meet. So here we're trying to send infinity to c comma 0, which is on the boundary of our upper half plane. So the two lines are still parallel. They don't accidentally meet somewhere on the upper half plane, still at the boundary. So what we're doing is we're trying to look for an invertible map that sends infinity to c comma 0. So you can pick your inversion wisely. Usually if you do your inversion, it sends infinity to 0, but then you can do an inversion and then possibly some sort of translation. These might come in different orders as well. So we want to send infinity up here to c comma 0. And then you can say, well, what about the other points? I mean, okay, well, if you want to send infinity to c comma 0, there's this inversion, and maybe you could do, a horizontal translation, but, that doesn't really give us the information about the other points. So what you can do is you can say, all right, well, infinity is the one point where L1 and L2 intersect, but you can say, all right, let's pick two other points. I'm going to call this point P1 and call this point P2.
Hello.
And here you don't have to be specific. You can just say, all right, I'm going to let P1 and P2 to be some point on L1 and some point on L2. The same thing over here. I'm going to pick this to be Q. Oops, actually, I'm not going to call it Q1. I'm going to call it P3 and P4, just so that all the indices are lined up nicely. So what I'm doing is I want to find a map that maps L1 and L2 to L3 and L4 in a very nice way. I'm trying to find this right conjugate. The thing is, now I have 3 points to keep track of. I have P1, P2, and infinity on my left, and I know that these are going to be distinct points because infinity is the point that's on both the lines. P1 is only on L1, P2 is only on L2, so clearly P1 and P2 cannot be the same, neither of them can be infinity. I want to send those 3 points to c comma 0, P3, and P4. So again, L3 and L4, the lines L3 and L4 are parallel, which means they only intersect at one point, which is going to be c comma 0, and then I have 1 point each on the lines. So here you can say, all right, well, I know there's this theorem that says, you have
你
a
直
distinct triple
不是你直接去拿
and
吧，我觉得
another
还是因为
distinct
你回来一
triple,
趟再过去，我们这来回太
there's
久了，你
always
回来
some
去正好
invertible
顺
map
便嘛。
that will map this triple
那
to
你
this
想吃
triple
啥？
in this specific order. Furthermore, you know,
不
the
行就
theorem that
铁
we
板
proved
掏
in
盘。
444 said,
就
okay, well, you know, if you have 3 points on
那
the
吃什么
Riemann
呀？
sphere and another, sorry, extended complex plane and another 3 points, then what you could do is you can always find fractional linear transformation. Here, you can further impose that this has to be an isometry by saying,
就是
okay,
你可以
infinity is
点
infinitely
鸳
far
鸯
away.
扒焗
An
饭这
ideal
种其
point.
实挺好的。
So P1 and P2 are infinitely far away from, actually, you know what?
对，
I'm going to drop the part about the isometry. Here, all we need is an invertible map to take conjugations. So what we're going to do is we're going to say, all right, well, whatever map you get as the composition of reflections about L1 and L2, if we call that map F, and then we're composing it with, you know, P inverse P, or in whatever order. I think it has to go in this order. Oops. This will give, let's say, G for some map. G will be the map that is the reflection about L3 and L4. And it will also give us a parabolic isometry that fixes C comma 0. So, you know, how do we do this in general? Well, we can't do this in like full-blown generality because there are different types of lines. But one thing you could do is, all right, what do I know about pairs of parallel lines? They meet at one point. So it's basically moving that one point around. Okay, if I want that one point to be at infinity, where the two lines meet, then the only option you have is two lines being vertical. So this is why I have, you know, x equals a and x equals b. I'm not even pinning down specific numbers for a and b. You can say any two pair of vertical lines. If you have a pair of two vertical lines, composition of the reflections of the two will give you parabolic isometry. The thing is, when you take parallel lines, they meet at one point. And the thing is, the parabolic isometry that you get from the composition of the two actually fixes that one point. I mean, I'm assuming, because the homework is due tomorrow morning, that you guys have tried something. I'm hoping that nobody's here just starting the problem. And you know, if you messed around with some of the lines, one thing that you'll notice, I'm gonna again make this assumption that you guys tried this one, where if you take L1 and L2 and you take the composition of the two reflections, what happens is you get a horizontal translation. And the horizontal translation, you know, if you take the matrix, it's, you know, you have ones on the diagonals, you have 0 on the lower left, and then you have some number on the upper right. And what happens is, you know, you get a map that's a translation by whatever number goes on the upper right, maybe z plus something, and that will be the parabolic isometry that fixes the point at infinity. You can say, well, everything's moving to the right or the left by some amount, nothing's being fixed, but the thing is, infinity is so far away where, you know, moving horizontally really doesn't change anything. So infinity, the point where the two lines actually meet, will be the point that's fixed. Same thing's going to happen with, you know, L3 and L4 or L5 and L6. Let's say if I do a reflection, let's say if I do a reflection about L3 and L4 in that order, first thing that's going to happen is L3 will just flip left and right. Everything on L3 will be fixed. Everything else will move. And then you apply the reflection about L4, which means everything outside the semicircle or above will go inside, and then inside will go outside. So what's going to happen is, okay, everything on L4 will be fixed, but then everything outside, even the stuff that were fixed on L3, will now, you know, go inside L4. The thing is, the one point that lies on both of the lines, you know, the C comma 0, where the two lines actually meet, will be fixed under both of the reflections. So, you know, we do a reflection about L3, we do a reflection about L4, but C comma 0 is always going to be there, whereas everything else is going to move around. You can say, well, all right, well, are you sure that everything's actually going to move around? Because, you know, when we do a reflection about L3, if we're switching left and right, but all of these things will come in here, and then some of the things will go out. The thing is, all right, well, what if it's like kind of tricky in like in the middle? Like, are we sure where it ends up? For example, if we, let's say, start from some point here and we do a reflection about L3, we end up here, and then we do a reflection about L4, it has to go outside the circle. All we know is that it goes outside the circle, but are we sure we end up somewhere else, or is there any chance that it'll go back to the original one? We don't know. We can't just like eyeball things and color the region and say this is going to go there, that's going to go there. The thing is, you can actually show that the trace of the whatever composition you get is exactly 2, or absolute value will be 2, and it'll tell you, okay, we only have one fixed point, and it's either at the boundary of the upper half plane or at infinity. Questions, comments? So there's like a lot of things that you'll have to fill up, because here you want to say, all right, let's say we have 2 arbitrary parallel lines. Here I'm saying, all right, here's L1 and L2, here's L3 and L4, possibly L5 and L6, and say, all right, well, if the 2 possible locations of our fixed point can be either off at infinity or on the boundary, and you can say, all right, well, if we have one point on the boundary, and that's where the 2 parallel lines are going to meet, well, what you can also do is you can say, all right, well, we can actually do a reflection about any 2 lines that go through that specific point. What does that mean? So here I'm starting out with this case because I think it's a little bit easier to compute this, but you can also say, all right, well, what if I want my pair of parallel lines to meet somewhere here? So parallel means they have to meet somewhere, but only on the boundary. So let's say you can have like a bunch of lines that go through this. And, we talked about this yesterday, and also this is in your homework 3, pencil of lines through a point at the boundary. So you can say, all right, I do know what their general form is. Pick any point on your on your real line and say, okay, we want to just call this x equals c. Or sorry, I keep writing x equals c. Say c comma 0. We know all the lines that go through c comma 0. We know the general form. Then one thing you can do is you can say, okay, I'm going to pick 2 of them. Say I pick this one and this one. So we have a formula for the reflection of each of these lines, right? Because what do we know? We know something about the radius of the circles, radius of the circles and the center of the circles. So one thing we can do is we can actually cook up a fractional linear transformation or a matrix with coefficients a, b, c, d to say, oh, if I pick certain lines, let's say if I pick this line to be, I'll stick to my colors and indices. If I pick L3 and L4 to be 2 lines that belong to some family, I can actually write down the fractional linear transformation, the reflection about these 2 lines. I know the radius, I know the center, that's our radius, center will be somewhere here and here. Given that information, one thing you can do is I'll write little r3 for a reflection about L3. I can explicitly find my coefficients to find the map. Explicitly find my coefficients to do the same thing for L4, R4. Beta, gamma plus delta. And here, we know that AD minus BC has to be -1 because we're looking at orientation reversing isometries. Same thing, alpha delta minus beta gamma has to be -1. So given just that information, and here, we're not picking just random coefficients. The coefficients come from the fact that the 2 lines are in fact parallel. And then you can take the composition of the 2 and compose one after another, or you can also say, oh, well, the coefficients of the product will actually come from the product of the two matrices. So you can multiply the two 2x2 matrices to get the coefficients for the composition as well. And then you can say, all right, well, the only thing that I, assumed was that L3 and L4 were in the same family of curves, namely pencil through C comma 0. And what I got when I took the composition of the two reflections, I got some 2x2 matrix, and the trace has, happens to have absolute value equals to 2. So that I covered it in different ways. I said, okay, first you can do the easy case and then send it off to something like this. But if you don't want to look at the two vertical lines because for whatever reason you don't want to, you can just say, all right, I'm going to pick a point, C comma 0. Here are the pencils. Here's the pencil that goes to that point. I mean, in fact, I guess what I did on the upper left is also looking at, two curves in the pencil through infinity. I pick infinity and say, okay, well, what are all the curves that go through infinity? It's just going to be all the vertical lines. Any questions? Oh, I have exactly half the class in my office hours. Didn't turn out. Does part B of both these cases make more sense, where I say, well, give me an explicit example? Let's see if that makes sense. Okay, I see some thumbs. How does everyone think about, providing explicit examples? Or is that also just kind of a... Oh, so when we look at okay, people are saying part 2 or example part is easier. So if we have a pencil, are all lines in the pencil family parallel to each other? Depending on what point we're going through. So usually people, use the word pencil for family of curves that go through a specific point. As long as that point is not on the upper half plane, then they will all be parallel to each other. If I, let's say, I think in homework 3, problem 1, I said write down the pencil through I, or actually any point on the upper half plane, you'll have a bunch of lines that go through that upper half plane. But if that point happens to be on the boundary, which is the real line, or at infinity, then that's the one point that they're all going to go through, either the point on the boundary or off at infinity. So for this case, if we're trying to pick two curves that are parallel to each other, meaning they will meet only at the boundary or at infinity, then you can say, all right, pencil through a point at infinity or at the boundary. Yes, they will be parallel to each other. Big 2 lines. I see. The pencil part is more intuitive than the part that I did on the upper left, which is also, fine too. Here, the one point just happens to be infinity, where here, the point is here. So I think if you pick a point or any point on the boundary of the upper half plane and say, can you draw what the pencil looks like? I mean, they're more or less going to look the same. They're just going to move around. Whereas the one off at infinity looks slightly different. And here you can say, well, what's the difference between blue and yellow? Well, there is really no difference. It's just, if I have a pencil through yellow like this, blue is just picking 2 lines where neither happens to be vertical. So there is not a huge difference between really the yellow case and the blue case. They're both just picking 2 lines from a pencil through some real number. do we need to find P inverse as well? So let's see what's happening over here. So here, I'm not actually finding the explicit P. What I'm doing, so this is the part. We want to prove this in the most general cases possible. So picking a specific point for P1 and P2, also P3 and P4, we'll prove for a specific case, but not for all of them. So here, what I'm going to do is I'm just going to say, let's just say I pick my P1 and P2 from L1 and L2 respectively. Let's say I pick P3 and P4, again, some points on L3 and L4 respectively. Then you invoke the theorem and say, I know there is some invertible map here. And okay, well, what about P inverse? Like, does that ever come into play? Well, let's think about what's happening over here. What do we know about P inverse and P? P is a map that sends, here we go. P is a map that does this. So highlight the ones in green. P inverse is the map that sends this, this, and this to this, this, and this. One of the first comments that I got when I ever taught a college level course was that I say the word this or something a lot in class. The thing is, I don't see the point of reading everything because it's just like a bunch of variables. It seems like a lot of words. If you're not paying attention, it's like easy to get lost. I don't know, I think. Anyway, these are the two things that we know, or a few things that we know. P sends the triple to a specific triple. P inverse sends a specific triple to a specific triple. And what we're going to do is we're basically saying, when we take the composition of the reflections of L1 and L2, see if this works. I can put more on the screen. If I take the composition of, let me step back. Before we take the composition, if I take the reflection about L1, let's say I'm looking at the reflection about, let's say L1 as, let's say R1, what it does is it fixes a line that goes through P1 at infinity, right? Everything else is going to move around. I'm going to pick 2 points. So I have a triple, but I'm only picking 2 of them, infinity and P1. Whenever you have 2 points, there is a unique geodesic that goes through the 2, and that line is actually going to be fixed. The thing is, when I map this through P inverse, when I map this through P and I go over to, my yellow lines or my set of yellow lines, what's happening is, right, P1 and infinity are set to, P3 and C comma 0. So I have 2 points there, and the reflection about L1 is now mapped to the reflection about L3, because I have 2 points. A geodesic is just defined. As soon as I give you 2 points, no one can argue which line we're talking about. The thing is, those 2 points are sent to P3 and C comma 0. So nobody can say, oh, well, there are more lines than just that one geodesic. Well, there's only one, which is in fact L3. So when I map this to L3, that's going to be the reflection that I actually get. So here, what I'm doing is, so the reflections are, well defined, and you can see that the reflection about L1 is mapped to the reflection about L3 to, through the map P, and then the reflection about L2, same thing with L4. Okay, then what is it about this P1? P inverse. So let's say P inverse is some map. And what it's going to do, you can think about it as the action going the other way, where we map the yellow lines to L1 and L2. So what's happening is this. I'm going to try to illustrate what's going on in this composition. What P inverse does is, don't even think about reflections. What P inverse does is it's going to map this triple to this triple. So you have your 3 points marked. Then you have your 3 points marked over here. What P inverse does is it maps the 3 points to the 3 points over here. Just maps it like that, and everything else will just follow accordingly. There's a unique fractional linear transformation that does the trick when you map the 3 points to 3 points. So first of all, we're mapping everything on the yellow side of my figures to the 2 vertical lines, so the very left side. And then what happens is F, which is composition of the 2 reflections. You do the reflections here on the left, and then P will send the points on the left on my white pairs back to the yellow pairs. And what that did was, you sent everything over here, you applied your parabolic isometry, and then you sent it back. And then what happens, all right, well, all these things are moving around, but the thing is, when we applied F was the map that fixed infinity. So while everything else moved around, when I was applying F, infinity was fixed, and through the map P, now this is being sent to C0, C comma 0. So what happened to C comma 0 is that C comma 0 was mapped to infinity through P inverse. Then the map F fixed that point. Then P sent it back to C comma 0. And we're saying that's the only point that was fixed because, we have F and G that are conjugate, and once they're conjugate and one of them is parabolic, the other one also has to be parabolic as well. So in either, while I'm saying all of this, the key is that F and G are conjugate to each other, which means they both have the same trace. P and P inverse, we're just saying, well, okay, well, I wanted to say that there is an invertible map that will do the trick. I'm never actually finding P. The reason why I know that this is going to be an invertible map is because of the transitivity on 3 points or on triples. If I have a triple mapped to a triple, this map, whatever it is, it's not gonna just like collapse and send it to a constant or anything like that. It's still an invertible map. And if this part you think you forgot, you can say, all right, well, if I have a fractional linear transformation, what was the one condition I was looking for? The determinant had to be non-zero, right? Invertible maps means that you have a map whose determinant is not equal to 0, in which case, whatever the inverse is, we do know that the inverse exists. Does that kind of make sense? Do we need to find the P or the P inverse? You can just say, no, I'm just going to say that here's a map. I'm going to just say P is a map that maps this triple to that triple, and we're not going to talk about what that map is. We just know that it exists, and we also know that the inverse exists. So that's all you have to say about P. Yeah, you're welcome. Wow, now I have more than half the class. So computation, you can make this really computation heavy if you want. I don't think it has to be that much computation. I mean, it also depends on what we mean by is this little or a lot? I think it's not as messy. If we, let's say, so I think it's a little bit less messier if you pick so we're going to have to start with the base case and say everything else is going to follow by conjugation. If you pick your base case to be the case where you have 2 vertical lines, then I think this requires the least amount of computation. Whereas if you pick what's on the lower right corner and say, well, I'm going to say my parallel lines have an intersection somewhere on the boundary of my upper half plane, then, I mean, these might look a little more complicated because, then we have to look at our general form for the curves in the pencil, which is really not that complicated. That might be a little more computation heavy than the 2 vertical lines, but no need to find P. All you have to do is just say that there is a P and the inverse exists, and everything else you can find by conjugation. So I personally don't think it's too much computation, but you'll have to write some things a little more than just English words. Will the transitivity hold for number 2? Or is that different? So number 2 is the case for ultra parallel, if I remember correctly. That will require a little bit. We can talk about that. Let me see if there's anything that I want to mention before I go into the ultra parallel case. Okay, so we don't have to compute or calculate P and P inverse. But do we need this to calculate the trace of G and trace of F? So there is this, so in terms of trace, so I hope I don't, there's something about ultra parallelity, which I'll get back to. There's something about examples. Here, computing trace. So the thing about computing trace is the following. So, oops. If I have, let's say, trace of, say, I'm going to take the product of 3 matrices. The thing is, product of matrices, I don't know when the first time you guys learned product of matrices, but it's like, oh, you take a row from here and you take a column from there and you multiply and add things on the way. It just seems like it's just an algorithmic thing that has absolutely no meaning. But the thing is, if you think about these as maps, if you think about these as compositions of linear transformations, well, then it makes a lot more sense. So this is why we look at products of matrices more often than sum of matrices. The sum of matrices, a lot of times, doesn't have any geometric meaning to it. All right. So unlike the determinant, where in the determinant, just the determinant of a product, let's just go back. If I say, hey, here are 3 matrices, A, B, and C, and you want to take the determinant of this, as long as A, B, and C are all square matrices, A, B, and C may not be square, but the product might be square. So let's say to define the determinant, we have to make sure all of them are in fact square matrices. This is just determinant of A times the determinant of B times the determinant of C. The thing is, all of these 3 things are numbers, which means we're multiplying 3 numbers. And of course, when it comes to multiplication of numbers, order doesn't matter. So, determinant of A, B, C moves the order around. The thing about trace is that this is, in fact, not equal to, you can't just change the order around like this. Like, this is not true. If I change the word trace to determinant, all right, it's still going to be true, even if the product ABC is not equal to BAC. I'm not saying matrix multiplication is commutative. The thing is, determinant of ABC is the same as the determinant of BAC, even if ABC is not equal to BAC, because the determinant of the product is basically going to be the same. It's going to be a product of 3 numbers. The thing is, when it comes to trace, this is not true. One thing that is true, though, is that when you have A, B, and C, you can keep that order, A, B, and C, and move things around, which means, while trace of ABC is not the same as trace of BAC, and spitting out a number, these numbers are different numbers. One thing I could do is I could shift the A to the other side so that ABC, let's say this is called cyclic permutation. Let's say if I keep saying ABC, 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 ABC this a million times, at some point it might sound like I'm saying BCA, BCA, BCA in that order, because it doesn't really matter. It's in the same order. That's basically what's happening. So this is why when we take the conjugate, let's say if I do something like this, oops, use capital so they look more like matrices. If P inverse is equal to B, which means A and B are conjugate to each other, then the trace of this, well, I can't just randomly change the order around, but I do know I can apply some sort of cyclic permutation. So let's say instead of starting P inverse, I write A first. I'll get something like this. In which case, now you can say, all right, this is what I have to find out, the product, and conveniently disappears because P inverse and P are inverses of each other. So this is trace of A. And here, P inverse B. So this is how we know that the trace of A is the same as trace of B if they're conjugate. We don't even have to know what the trace of P is. Like, we don't have to compute P. we don't have to know what the trace of P is. We don't have to know what the trace of P inverse is either, because we know if A and B are conjugate, they give us the same trace. Another thing about for example, so each of these cases I'm asking you to do something for parallel lines and something for ultra parallel lines. For parallel lines, just pick 2 lines that are parallel and just show me that, okay, you do something theoretically and you prove for all general cases, but I can also give you 2 lines and show you that's true. So I just want you to give me some like actual lines with numbers for the second part. For the ultra parallel case, it's a little bit trickier because they don't actually meet, right? With the parallel case, the lines have to meet somewhere, either at infinity or somewhere along the boundary. The thing is, all right, ultra parallel case, that's not even true. So let's look at all the configurations that we can get in the ultra parallel case. Which means even if you extend these lines, they're not going to meet. So if I have a vertical line, what I mean by extension is we think of this as going all the way up to infinity. So we just want to avoid the infinity part. So that means if I do have a vertical line like this, it's going to blow up to infinity. My other pair that's going to give me a pair cannot be vertical. If I have 2 vertical lines and you say, oh, they don't meet, the thing is, well, they will meet at infinity if we extend it. So that's not included. So no vertical lines whatsoever. So I can have something like this. And then I could also have something like this. So on the left is a parallel case, ultra parallel case. On the right side is also an ultra parallel case. The thing is, they don't fix a point, right? If I say, all right, how do I pick out parallel lines? You can say, I'm going to pick a point somewhere on the boundary or somewhere off at infinity, and then pick 2 lines that go through it, or pick 2 hyperbolic lines that go through it. The thing is, well, now we don't have that, right? Because they don't have anything in common. They don't meet at infinity. They don't meet anywhere. So here you can do a little case by case, or you can try to apply the logic. But this is how I would probably go, because I can't have like a family of curves that go through anything. There is no point. I might split this up into 2 cases and do something like this. All right, let's say this is x equals a, and I don't know what this line is going to be, but let's call this point c comma 0 and the radius r. And then what I can do is I can say this is L1, L2. You can use x and y variables if you want, or you could also say this is a collection of all the complex numbers centered at z with radius r. Or you could just write it like this. One thing we know about these 2 lines is that, okay, we don't really know a lot, but one thing we know is that the distance between a and c comma 0, or a comma 0 and c comma 0, this distance, I'm taking the absolute value, has to be greater than r. Because if they're exactly r, then, well, if there is an equality, then it means the 2 lines are going to be parallel. If the inequality goes the other way, that means the 2 lines will intersect on the upper half plane. So this is the one assumption that we're going to have. And then you can say, all right, well, I actually do know how to write down reflections given the line. Or, if I'm given a reflection, I can actually write down what the line is. So from that information, you can say, all right, well, what is the fractional linear, what is the reflection about L1? Call that R1 with, okay, I already used ABCD up here. All this is star. All this triangle. Let's call this square. Whatever your star, triangle, or square are, you get your reflection about R1, AB, reflection about L1, excuse me. And then you get another reflection about L2. Here our determinants must be -1. They're all -1. And whatever these coefficients are, they come from the lines, whatever star, square, and triangle. The thing is, when you take the composition of the two, you'll get some other more complicated form. You take the composition of the two in whichever order, what you're going to get is, again, something z bar, or some. Now we'll get a hyperbolic isometry, an orientation-preserving isometry. All these spirals may be different, but we get something like this. And the thing is, when we compute the trace of this, and we say, I'm going to add these two numbers together, the thing is, there will be some data. I mean, A, B, C, D, alpha, beta, gamma, delta have something to do with star, square, and triangle. That information is actually going to show up on the trace, and you will be able to show that the trace of whatever here is greater than 2 or less than -2. And here we have this inequality because of the inequality here. If this happened to be, equality, then this will be equality 2. The thing is, that's not what we're looking for. We're looking for this range. Then you can do a similar thing on the left-hand side as well. Here, have two semicircles. One thing we know is, okay, well, you can find out, you can say, oh, I'm going to pick a random center C1. Okay. If I use a C, that's going to show up on my fractional linear transformation. Let's say that's C1, C2. Let's say this has radius R2 and this has R1. One thing we know about ultra-parallel lines is that here we will want C1 minus C2, or the absolute value of that, to be at least R1 plus R2, right? Because we don't want them to intersect even on the boundary of our upper half. So given this, find your respective reflections, take the composition, then you say, all right, here's the composition of the two orientation reversing isometries, but you did reversing twice, back to something preserving. The trace of the final orientation preserving isometry must have a trace whose absolute value is greater than 2. Yay, and then we're done. Is there a case where, oh, wow. Is there a case where the circle is inside another? I haven't thought of that. I'm glad nobody left. That's a great point. Why didn't I think of that? Thank you. Something came in private message, so respect privacy. Somebody said, what if the two circles are like this? This is great. Now, come to think of it, you know what? In the earlier picture, I'm going to scroll up really quickly, so hang on tight. I was looking at the yellow case and the blue case. I didn't draw this one, or I didn't actually pick it this way. Or let me focus on this figure over here on the upper lower left. Here, I picked my two yellow curves, L3 and L4, to be kind of on the other side of the vertical line. But you could have actually, or I could have actually picked this too. So let's leave one here and call this one to be L4. This is still parallel because they meet at one point. Good point. But it still doesn't change the fact that they're still from the pencil family. So ultra parallel case, yeah, this is also a case that would work. I'm going to do some exaggeration here. In this case, let's see if we actually get some bound like this. So had a bound like this that said the difference between the distance between the two centers of the Euclidean circles is greater than R1 plus R2. Let's see if we get something similar down here as well. So we have to prove case by case. At the moment, I think that's what we're doing. Because with parallel cases, you can basically what you can do is you can find a point, an ideal point, and say, I'm going to look at the pencil of curves through this point, and then just pick two from the family. For ultra-parallel cases, it's a little bit harder. You can't fix a point and say, I'm going to look at the lines that don't go through this point. It's not exactly that. But great questions. Call these centers C1 and C2 and see if there is any sort of bound that I get from R1 and R2, which are going to be my radii. So let's call that R1. Let's call this R2. And if I don't want, so here, think about this, the circle inside, kind of moving around like this. How far can it go? Well, we don't want it to touch on the left, so it can only go like that far. But also, it can be anywhere in the middle, but it can go like all the way up till there. So let's see if there is some bound I can find. Let's say the circle is on the right side, or C2 is greater than C1. So let's say I have that one. The other case, I don't think you have to do this all case by case. I'm just going to make sure that the circle is on the right side. So I move around. And the thing is, it's totally fine until I get up to a certain point. And what is this point? Here, what we want to do is we want to say this distance between, if we're assuming that C2 is actually greater than C1, can do this. C1 minus C2, which is the difference or the distance between the two centers is, or plus 1 is less than this is R2. R2 is less than R1. The earlier bound that we had looked like this. Let's see if I can pull this down here. Oops. Sometimes it does. Oh, there we go. Long enough. So this was the previous case where I said this, but let's just, keep C2 greater than C1 so we don't have to worry about absolute values. This is the inequality that we got. Now, in our second case, we have an inequality like this. So what can we say about this? We have C2 minus C1 is less than R1 minus R2. And here we're assuming that R1 is greater. I guess this has to be within a certain bound. It has to be less than the difference between C1 and C2 has to be bounded below by the sum of the radii. So this is going to be a greater number than what we have over here, right? Because if we have two positive numbers and we take the difference, well, the sum must be greater. This number is greater. We want the difference between the two circles to be either large enough so that the two circles are outside of each other, or they're close enough so that one circle is strictly inside. Does that make sense? On finding examples, whatever examples are fine, just give me two lines that are parallel or ultra parallel for each of the cases. Pick your two lines, write down the reflection about those two lines, take the composition and say, hey, the trace here is a number, which has absolute value exactly equal to 2 or absolute value greater than 2. Whereas, in the more general case, there will be fewer numbers, I guess. the way you pick your lines. For the example case, well, I guess I wouldn't want to see like x equals a and x equals b. These aren't explicit examples. I want you to give me numbers for a and b and find the actual orientation reversing isometry, so a reflection, and then like actual computation of the composition. You see if there's a way to do this. It's kind of like the previous case, because the case where we have parallel lines, it looks like just have a pencil, you could pick your curves from the family. In the ultra parallel case, let's think. The only thing that comes to mind with the ultra parallel case, and this is just me just blabbering, so I don't even know if this is going to make sense. The thing, because I'm trying to think about the pencil cases. So in the parabolic case, we had a point somewhere, and then we had curves like this. Or if the one point was at infinity, we had a bunch of vertical lines. Do we need an example for 1b and 2b? Just one for parallel and one for ultra parallel. It doesn't have to be for, if the two parallels have a point here, you just show me one pair of parallel lines and one pair of ultra parallel lines. So this is the parabolic case. The hyperbolic case, we don't have a pencil really, but we do have a gamma. And as I said just a minute ago, this may not go anywhere. I'm just trying to see if there's if there's like one way that will cover all the hyperbolic ones. So in the parabolic case, you just say, oh, here's a point. Here's a pencil, a family of curves. I'm just going to pick two random elements. In the hyperbolic case, well, we have 2 points. And how do we pick our 2 curves? I feel like hyperbolic has a wider range of curves to pick from, because they're parallel, they meet somewhere, but anything else that doesn't meet. It's like if I have, let's say, 2 semicircles, I can fix one, and then the other one can just go as far as it wants to. So I'm starting to think that there may not be like a quick way of picking curves because of the range of curves that you can actually pick. Questions? You want me to scroll up or go over a particular part one more time? Let me know. If this picture isn't very helpful, maybe I'll scroll up a little bit. Parallel. Well, if there are no questions, this is when somebody would be like, wait. Right. I think I said everything, but you may disagree. So if you disagree and you want to get more out of it, let me know. I'll wait for a second, and if I feel like we're all kind of dead inside, I'll just end the meeting.
One quick question.
Yeah.
So for the example you are asked to give, we only saw one case is fine, right?
Yes, one parallel pair and one ultra parallel pair, and then just don't just write down the lines and say this is a parallel pair, because I'm asking you to actually verify. Write down a pair of parallel lines. Write down the reflections. Write down the composition of the reflections. Show that the trace is 2. For the second one, just give me an example of ultra parallel lines. Write down the reflection about each of the lines, write down the composition, and then show that the trace has absolute value greater than 2.
Okay, thank you.
I knew it. Like, all right, I'm going to go. And then somebody was just going to be like, wait, last minute question. Okay, let's do it one more time.
I'm sorry.
Yeah.
For the proving part,
Mhm.
for example, for the auto parallel,
Mhm.
there are 3 general cases. So we prove it. There's 3 general cases in the
Mhm.
first part. And for the second part, we just select any one is fine.
Yes. Whether it's the vertical and the semicircle that don't meet, or the 2 semicircles that are far away from each other, or whether it's this case where there's like one inside that doesn't touch the one outside. Yeah, just give me one. You don't have to pick for all 3.
Okay.
Yeah.
And for the general one, we just prove we calculate the matrix for the first reflection and calculate the matrix for the second reflection, and compute the multiplication of this, and say the trace, the absolute value of the trace of this, the matrix after the multiplication is greater than 2 or something like that.
Yeah.
Okay, got that.
Mhm.
Thank you so much.
Yeah, you're welcome.
Thank you. Have a good day. Bye.
You're welcome.